Welcome back, students. In this video, we are going to look at the E1 mechanism. The first thing that I'd like to do is look at the definition of what E1 stands for, and then we'll go into talking about the rate equation, the substrate structure, and regeo and stereochemistry. The E in E1 stands for elimination. Remember that we said that we're eliminating one group and also a beta proton. So the leaving group is leaving and we're removing a beta proton. And then what will happen is we create a pi bond at the end. The 1 stands for unimolecular, which means one compound is in the rate equation. Let's look at that rate equation. When we are looking at the rate equation, we need to also consider the mechanism. The first thing that happens in the mechanism is the loss of the leaving group. So the leaving group leaves and it forms this carbocation, and then your base can come in, pull off a proton, and then form a pi bond. Unimolecular means that your rate equation only depends upon one compound, and that one compound is going to be this, which is what I call the substrate. Other people will call it just RLG, so that they're communicating that it's the alkyl compound that contains the leaving group. We can write the rate equation by writing rate equals the rate constant times the compound that contains the leaving group. That means that no matter how much base you add to your reaction, it does not speed up anything. Your rate limiting step or your rate determining step, the thing that determines how quickly this reaction can go, is how fast the leaving group leaves. Because as soon as you make that carbocation, bam, that base is going to react with it, but you have to make the carbocation first. So if you increase the concentration of the base, no change to the rate. But if you increase the concentration of the substrate, which is the thing that has the leaving group on it, yeah, the rate's going to increase. Let's talk about that substrate a little bit more. What's going to happen in this reaction is a base is going to come in and abstract a beta proton. First, we need to talk about where the beta proton is. When we consider what's happening, your leaving group is leaving, and you end up creating a carbocation. That carbocation has to be stable in order for it to form. If we focus in on the carbon that bears the positive charge, that's the carbon where the leaving group used to be attached to. The leaving group has since left. We've made the carbocation, and now we can look at this and start classifying as methyl. And then remember, this one is primary because there's only one carbon group attached. So this is primary. Here we have a secondary carbocation because there's 2 carbon groups. And then this one is tertiary because there are 3 carbon groups. When we talked about carbocations in a prior video, we said that we're increasing stability going this way. So tertiary carbocations are more stable than secondary, which are a lot more stable than primary, which primary essentially don't form. And then methyl is the worst carbocation. What this means for us for the E1 reaction is we need a hindered substrate. We need something that is going to form a stable carbocation. So we need something that's tertiary. We could get away with something that's secondary. We could definitely do allylic and benzylic. And even if you have an allylic, it could be a primary allylic, that would be okay. But primary on its own, not going to happen. Methyl on its own, not going to happen. So we need something that's going to form a stable carbocation in order for this reaction to happen. Remember that because you're dealing with carbocations here, you also need to be on the lookout for carbocation rearrangements during these reactions. So whenever you form a carbocation intermediate, you have to pause and think, can this rearrange to form something more stable, yes or no? We'll talk about that some more in an example video later on. Let's consider regiochemistry. Remember when we talked about regiochemistry in the past, we said regio stands for region. So we're looking at the different location that a pi bond is going to form in our structure. When we consider this reaction, now in the E1 reaction, what happens first is your leaving group ends up leaving. You create a carbocation. And then where your carbocation is, I'm going to put a blue dot on that. That's your alpha carbon. Your beta carbons I will highlight in yellow. Two of these beta carbons are very similar and one is different. The one that I'm going to highlight over in blue to make a kind of green color, that one is the one that's different. The two that are yellow, those are equivalent to one another. They're both on a methyl. And what that means is when we pull off a proton either here or here, we get the same compound at the end. Whereas if we pull off a proton here, we would get a different compound. When we're looking at the base removing a proton, notice how the base here is different. It's water. Before I had negative bases. When we're talking about E1 reactions, you don't need a strong base. You can use a weak base because carbocations are highly reactive. What's going to happen is your base is going to come in, it's going to pull off a proton. It can pull off this one, and you could get a product that looks like this. Or, I'm going to draw this in a different color. You could have this proton get removed and get a base and get a product that looks like this. Zaitsev rule, which says the more highly substituted alkene predominates, means that this one is going to be your major product, and this one will be your minor product. In our last video, we talked about how to decide if we had a more highly substituted alkene. Remember what we did was we looked at the carbons that were sp2 hybridized, we highlighted them, and then we said we had 1, 2, 3 total carbon groups attached to those. So this was a tri-substituted, whereas over here we had 1, 2 carbon groups attached, so that one was a di-substituted. More highly substituted alkenes are more stable than less substituted alkenes, and so these are going to be your major product, the more highly substituted alkenes. Let's look at stereochemistry. Both trans and cis alkenes are possible in certain situations. If you have a substrate that has a beta carbon where you have more than one proton available, what that means is you can get both cis and trans alkenes as your products. So if we look at this position, we could pull off this proton and actually get both the trans and also the cis product. In addition to that, we could technically also pull off this proton, but then we'd be talking about regiochemistry. If we talked about regiochemistry, we would end up with this product if we pulled off the green proton. Out of all three of our possible products, the one that is the major product is this one. It is the more highly substituted alkene. So regiochemistry-wise, it is the better of the two sets. And then within being the more highly substituted alkene, it's also trans. Trans is going to be the more stable product over the cis. So the one that I've labeled as major is major, and the other two we would consider to be minor. Let's wrap up. In this video, we looked at E1 reactions and we considered how they are stepwise reactions. We also reminded ourselves what unimolecular meant, which was one compound in the rate equation. For these reactions, you need a hindered substrate, something that's going to form a stable carbocation. And because you're dealing with carbocations, you have to watch out for carbocation rearrangements. For regiochemistry, the more substituted alkene is going to predominate, and for stereochemistry, your trans alkene is going to predominate over cis. Thanks so much for watching. This is Katoni signing out.